Welcome back to IED. Today we're going to be talking about geometric shapes and area. Shape is something that describes a two-dimensional contour that characterizes an object or area, in contrast to a three-dimensional solid. Examples include circle, ellipses, and triangles. Whenever we talk about something that's shape stands for area. And that's one of the things I want to really point out here is that sometimes I hear students say, well, is it a box-like shape? Well, it can't be a box-like shape because box is a three-dimensional figure. So area and shape are really talking about the same thing. Area, all right, slash shape. I'm trying to get a pen up here. Slash shape. Area is the extent or measure of a surface. All shapes represent enclosed two-dimensional spaces and thus have area. So circle is the shape, the stuff inside it is its area. Circle is a round plane plane figure whose boundary consists of points equidistant from the center. And what that means is if we were to draw a line here and go out here, let's say 1 inch, draw a point, and just start drawing a bunch of points that were 1 inch away from that circle. Pretty soon, if we drew enough of these points in, you start to get a shape that we describe as a circle. They would all fit around this circle here, and that's what we mean by equidistant. They're the same distance. Okay, some information that we need to know about circles. The circle is the simplest and strongest of all shapes. Circles are found within the geometry of countless engineered products, such as buttons, tubes, wires, cups, and pins. A drilled hole is also based on the simple circle. Area of a circle. All right. Area of a circle, our equation for the area of a circle is pi r squared. And this is area of a circle. You're going to see me use a lot of these subscripts here. I'm going to try to get you guys used to these subscripts here. Area of a circle. All right, again, area of a circle is pi r squared. Pi is 3.14. R stands for radius. A stands for area. Okay, an ellipse is generated by a point moving in a plane so that the sum of its distance from the 2 points, the foci, is constant and equal to the major axis. So what we look at here, then, in this ellipse, we've got some things let's talk about here. First of all, I want to talk about the foci. All right, here's a focus, there's a focus, and if we put those together, it's called foci. We have a minor axis. The minor axis is the axis that goes from one skinny side to the other skinny side. The major axis is the axis that runs from the distance of the widest distance. Right? If we change our ellipse and make it be like this, then here would be the major axis. This one here would be the major because it runs the distance that is longest. It's important to be able to identify those because to calculate the area of an ellipse, the lengths of a major and minor axis must be known. Our minor axis, we define the distance from the center to the skinny end as b. So the minor axis is 2 of these, henceforth it's 2b. And that's why we have this equation down here. The major axis, we can consider the distance from the center to the end as a. So 2 of those gives us the major axis, henceforth 2a. And that's that equation. So we're giving you several equations here. Again, this is an area of an ellipse. Pi is 3.14 and A stands for area. Polygon is any plane that is a plane figure bounded by straight lines. Examples include the triangle, the rhombus, and the trapezoid. All right, so these are all 3 polygons that are in any plane, meaning they're just flat. All right, they have no depth. They have a base and a height. The base and a height is how we define them. Angles. An angle is the figure formed by the intersection of two rays. Angles are differentiated by their measure. We have several different types of angles here. First of all, we have an acute angle. All right, acute means it's less than 90. Or right means it's exactly 90. Obtuse means it's between, here'd be 90, here'd be 180. So obtuse means it's going to fall in this range right here somewhere. It's greater than 90 but less than 180. And then a straight angle is exactly 180. Triangle is a three-sided polygon. The sum of the interior angles will always equal 180 degrees. Triangle is a three-sided polygon. The sum of the interior angles will always equal 180 degrees. So what that tells us then is that if we take the three angles here, I'm going to say A, B, and C and add them up. A plus B plus C, that's going to equal 180 degrees. So if this one's 30 and this one over here is, let's say 50, then we know that that one has to be 180 minus 50 minus 30, which gives us 100 degrees. So that angle right there would have to be 100 degrees because any triangle, the interior angles are always going to add up to 180. Okay, all triangles can be classified as one of these three triangles. All right, a right triangle meaning it's got one right angle in it. An acute triangle, it means all the angles are acute or less than 90. All right, all of these angles are less than 90 degrees. Obtuse triangle, one interior angle is an obtuse angle, which means one interior is more than 90 degrees. Triangles. The triangle is the simplest and most structurally stable of all polygons. This is why triangles are found in all types of structural designs. Trusses are one such example. We'll talk a lot about trusses in your next level class. Now some of you might say, well, the triangle, they just said the triangle is the simplest. The circle is the simplest and strongest of all the shapes. A triangle is the simplest and most structurally stable of all polygons. Well, shape, polygon, what's exactly the difference again? I've kind of forgotten. Let's go back. A polygon is any plane figure bounded by straight lines, and there's the difference. All right. So this is why out of the triangle, the rhombus, the trapezoid, the square, anything that you were to, any polygon, the triangle is the strongest of those objects. All right, triangles and circles. All right, I'm not going to spend a lot of time. Inscribed. All right, inscribed. This means the triangle is in. All right, the triangle is in. Circumscribed. All right, well, it's kind of if I look at it and say inscribed means it's inside. If it's not inside, then it has to be circumscribed. And that's kind of how I remember that. Area of triangles. All right, they give us lots of information here, but really the area of the triangle, I'm going to use a little subscript here again, the area of the triangle is 1/2 the base times the height. The base and the height. The height is straight up. We measure that at a 90-degree angle. Okay, quadrilateral. Quadrilateral is a four-sided figure, polygon. It's got these straight lines and it's got four sides. All right, so it's a polygon, so it's got straight sides, and it says quad, so it's got four straight sides. We have parallelograms. Parallelogram is a four-sided polygon with both pairs of opposite sides parallel. All right, so these are all parallelograms. A rhombus, a rhomboid, rectangle, square, because opposite sides, these opposite sides are parallel, right? And then the other opposite sides are parallel. So these right here are all parallelograms. Our equation to find the area of a parallelogram, again, is we take base times height. That's the same as it is for a square. Well, yeah, because the square has a base and a height. So parallelograms are squares. That's why the equation for that is base times height. Well, it's the same thing for a rectangle. Well, that's because it's got a base and it's got a height. We like to think it's the equation for a rectangle. It's really the equation for all parallelograms, right? Whether it's a rhombus or a rhomboid. It's not just the equation for the area of a rectangle. It's actually the equation for the area of all parallelograms. Well, hey, hopefully that was informational. I'll catch you guys on the flip side.